Yeah, so welcome everyone to the second talk of the third season of the Isogeny Club. Today we have Tomoki Moriya giving the talk. He's a PhD from the University of Tokyo, and he's working as a research fellow at the University of Birmingham. So yeah, please take it away, Tomoki.
Okay, thank you for introducing me. The title of my presentation is The LIT Problem and Ice Cube. And I'm happy to talk to you here about my recent research. Oops, sorry. Okay, first I summarize my about this talk. And I first propose a new computational problem named the LIT problem. And this problem is a new problem, but it's almost same as a CSSI problem. It's a problem for the SIDH. The difference between the CSSI problem and the LIT problem is the restriction about the order of the torsion point and the degree of phi. So in other words, it is a problem of computing a hidden isogeny from two elliptic curves and image of torsion points of order relatively smaller than the degree of the hidden isogeny phi. So from E and E prime and P and Q and phi P and phi Q, and the order P is relatively smaller than the degree of phi. Then in this situation, the compute the hidden isogeny phi. This is a LIT problem. Today, I introduced the LIT problem and explain some analysis of the hardness of this problem. And next, I propose a new key encapsulation mechanism named Ice Cube based on the LIT problem. And the property of the Ice Cube is, first, we can use the prime about 2 to 8 lambda prime for the security parameter lambda. And second property is we can use a random super singular empty curve as a starting curve. Okay, this is an easy summary of my talk today. And here are contents. And first I talk about background. And second, I introduce the LIT problems and talk about the analysis of this problem. And finally, I explain the construction of Ice Cube. This is the contents. And first, I explain about the background of this study. First, I explain about the SIDH. I guess everyone here is already known about SIDH, but I talk about a little. Set the prime P as the P equals the LA to A times LB to B times F minus 1. And here, LA and LB are small integers, and they are prime. And F is a small integer. And in this case, we can construct this commutative diagram. And phi A is the isogeny, and its kernel is generated by PA plus alpha QA. And phi B is isogeny, and its kernel is generated by PB plus beta QB. And at the beginning, I will compute this phi A and output the image of the isogeny and the image of the points of PB and QB. And Bob also compute this isogeny, and he outputs the elliptic curves and the image of torsion points, phi BPA and phi BQA. And finally, they exchange these isogenies, then they can construct the other two isogenies, and they share the same elliptic curve. And this is a SIDH key exchange. And one property of the SIDH is we could take P such that the P is about the 4-bit prime. It is because the degree of the isogeny phi A is can take the 2 to 2 lambda, and phi B is also the degree of 2 to 2 lambda. So the size of P is about 2 to 4 lambda. And this is one reason why the SIDH was compact key exchange scheme. But unfortunately, as you may already know, the SIDH was broken in 2022, and here is for the attacks for SIDH. But some other isogeny-based key exchange or PK schemes are still alive. For example, Seaside is still alive, and some isogeny-based one proposed after breaking SIDH, for example, M side and FESTA and TAR side, are still alive. So isogen-based key extension PK schemes are alive. However, the most of scheme of the primes appearing in the most of schemes are not guaranteed to be rated linearly to lambda. And I showed an easy example. For example, C side, when the security parameter is 128, the bit length of P is about 3072. I took this number from the paper titled The Scope of C side, Sublinear Bell Quantum Resistance Isogeny Axon with Low Exponents. And when the security parameter is 192, the size of prime P is about 8192. So the ratio of the bit P and lambda is in security parameter is 128, it is 24, and the 122, it becomes 42.69. So it is not linearly rated to the bit prime. Another example is M side. And M size is also seen not rated linearly lambda. And other example is FESTA. FESTA is not good, but not so bad, but it is not linearly rated. And also it's not guaranteed to be linearly rated. Then I thought, and the most scheme is not guaranteed. So in other words, there's a exception of this type thing. And I know there are two exceptions. First one is FESTA HD. This is not a common word I introduced in this talk, but this is a FESTA using the isogenies of dimension 4 or 8. And other one is QFESTA. And QFESTA is very recently proposed by Nakagawa and Onuki. And FESTA HD, we can use the prime of size about 7 lambda bits. However, there's no implementation. I should say so far, but there's no implementation due to the computation of the high dimensional isogeny. It means the isogeny of the dimension 4 or 8. And I guess therefore, I guess many people want to avoid the high dimensional computation for many reasons. So this is a problem for FESTA HD. And other exception is QFESTA. Then QFESTA can use the prime of size about 2 lambda bits from their cream. It is not so good. It is very good. But QFESTA need to use the curve of J invariant 1728 as a starting curve. So as you may know, the curve of J invariant 1728 has knowledge of its endomorphism link. So there's a potential risk for security. So this is a one demerit or problem for using QFESTA. So for we or only me or some high dimensional and J invariant 1728 want to a scheme with the prime P whose size is linearly related to lambda, and using a random starting curve as a random starting curve, and use a computation of isogeny towards not 4 or 8 dimensional isogenies. So this is this research question, and the answer of the question is the LIT problems and IceCube. And IceCube satisfy these 3 properties. Okay, this is a very easy background of my study. And next, I want to introduce the LIT problem. And before talking about the LIT problem, I guess I need to talk about the SIDH attacks. So first, I introduced the CSSI problem. It's a problem for SIDH. And let P be a prime such that P equals large A times B times F, and A and B are smooth large integers, and these are coprime, and F is a small integer. And let E and E prime be a supersingularity cups over P squared, and phi is an A isogeny. And let PB be a basis of the P torsion subgroup of E. And in this situation, from E and E prime and PQ and phi P and phi Q, compute the hidden isogeny phi. This is the CSSI problem. And the Lovel's attack solved the CSSI problem if A is smaller than or equal to B squared. Then I explain how this attack solved the CSSI problem. And first I defined the isogeny diamond. Isogeny diamond or SIDH diagram is a diagram used in the SIDH. So this diagram is a isogeny diamond. And precisely speaking, let A and B integers such that they are coprime. Let E be an LD curve, and let R and R be subgroup of E of order A and B respectively. And we can construct this commutative diagram. And we call this commutative diagram an isogeny diagram or SIDH diagram. Okay, then we think by using this concept, we can state the Kanish theorem. It is a very important theorem for adapting SIDH. And this theorem also used to construct for ice cube. So please don't forget about it. And let there's a SIDH diagram. And let PQ be a basis of A plus B torsion subgroup of E. Then here's a statement of the Kanish theorem. First, there's a isogeny psi defined by hat phi A and phi B and phi B prime and phi prime defined by the 2 times 2 matrix. And this is isogeny from E1 times E2 to E times E3. And the statement is the kernel of the isogeny psi is generated by phi AP, phi BP, and phi AQ, phi BQ. So this is a Kanish theorem, and this theorem says if there's information of the torsion points of order A plus B, we can compute the isogeny between E1 prime, E1 times E2 to E times E3. This is a statement of a Kanish theorem. And we use this theorem to attack SIDH or solve the CSSI problem. Okay, the next I'll talk about the strategy of the Lovel's attack. First, we compute the integer C as defined by B squared minus A. And next, we find four integers, C1, C2, C3, C4, such that the C squared equals C1 squared plus C2 squared plus C3 squared plus C4 squared. We can compute these four integers by using the 4 square theorem. And next, we construct the 4 times 4 matrix C over Z, such that the transpose of C times C is become to small c. This is the integer computing here, times the I4. The I4 is the identity matrix, and then we can construct such matrix C by using the C1 to C4. And then we consider the SIJ diagram of high dimension like this. The horizontal isogeny is come from the phi A, and the vertical lines come from the matrix C. So we can consider this SIDH diagram. The Lovel's attack is attacked using the Kanish theorem for this SIDH diagram. So from the Kanish theorem, we first have the isogeny of the dimension 8 defined by this. And the kernel of this psi is constructed by using phi A, EB squared and EB squared. It is because we take C as the B squared minus A. So considering the concerning this isogeny, we can construct it by the B square torsion points. And by thinking similar way, the kernel of the hat psi is also constructed by B square torsion points. So we can compute psi by using BP, QB, and phi BP and phi QB. These are the B torsion points. At first, we compute the half of the psi here. And next, we can compute the half of the dual of the psi here. Then we can find, then these two isogenies go to the same abelian variety. Then we can compute the whole isogeny here. So this is a way to compute psi by using B torsion points. And from the concern, we know the psi is defined by phi A. So after we can compute psi, we also compute phi A. So this attack solves the CSSI problem if A is smaller than or equal to B squared. This is a very easy explanation of the reverse attack. So there are some countermeasures of this type attacks. And the first countermeasure is the hide the information of the degree of phi A. This is related to the MD side. The other approach is the hide the information of the torsion points by some scalars. That is related to the M side and Festa. And other approach is set A is larger than B squared. And this is a new approach to construct the scheme. And this is related to the LIT problem and ice cube. Okay, and so yeah, this is a new approach for the countermeasure of the SHH attacks. Okay, then I want to explain the LT problem, but I guess I should explain the CIST problem before I introduce the LT problem. So I explain the CIST problem. It is a problem of Festa. Let P be a prime such that the P equals A times B times F minus 1, where A and B are smooth large integers, such that these are coprime, and F is a small integer. And let E and E prime be a supersingularity cups over Fp squared, and let phi is an A isogeny, and let P be a basis of EB, and let alpha be a random element in the unit group of Z over BZ. Then the CSI problem is a problem to compute the hidden isogeny phi from E and E prime and P and Q and alpha phi P and alpha minus phi Q. So here we hide some information of this torsion points by using the alpha. Now, this is a CSI problem, or I should say it is a simple CSI problem. If you want to know to the precise version of the notation CSI problem, you should read the original paper of Festa. But this is a CSI problem. Okay, so then next I want to explain about the LIT problem. And the LIT problem is the long isogeny with torsion problem. The situation is almost same. There's a P and AB and smooth and coprime, then F is small integer, and E and E prime be supersingularity curves, and their isogeny, and PB be a basis of AB. And this is a problem to compute the hidden isogeny phi from E and E prime and PQ and phi P and phi Q. But here's a restriction of the degree of phi and B. Degree of phi is extremely larger than the B. It is the order of the points of PQ. Okay, this is a LIT problem. However, there's a question when this problem is hard to solve, because this statement does not say anything about the relation between the degree of phi and E. So there are possibility, for example, degree of phi is almost same as B cube, or degree phi is almost same as b squared times 2 lambda, or more than larger. So there are many possibilities, the relationship between the degree phi and b. So the question is that when does the LIT problem seem hard to solve? The next I explain the analysis of the hardness of this problem. Then I provide two strategies to solve the LIT problem. And first strategy is find points P prime and Q prime and the image points of them. And order of the P prime and Q primes are B times large N. And it satisfies the degree phi is almost same as the B N squared. And NP prime is equal to P and NQ primes is equal to Q. So after we can find the P prime and Q prime and phi P prime and phi Q prime by using a Lobel's attack, we can solve the LIT problem. This is the first strategy. And second strategy is to combine the Lobel's attack and using the meet in the middle attack. By using the point PQ and phi P phi Q, we can construct the two isogenies from E4 times E prime 4 to some polarity V, and other one is E4 times E prime 4 and go to the some polarity V prime. In the case of the attack for the solving for the CSSI problem, the polarity V and V primes are the same, so we can recover the isogeny between the E4 times E prime 4 and E4 times E prime 4. But in this case, the V and V primes are not the same. So to connect these polarities, we use the meter in the middle attack in here. Then we can find the whole isogenies between them. And by using this isogeny, we can recover the hidden isogeny. This is the second approach to solve the LIT problem. Okay, then I explain the first approach to solve the LIT problem. This is find points P prime, Q prime, and the image points. And if we fix some nice spaces, P prime, Q prime, then the number of the candidates for phi prime P and phi P prime and phi Q prime is the number of the PJL2 Z over NZ. And this is a projective general linear subgroup, general linear group over Z over NZ. And by general theory, we know that this number is larger than the large N. So we prefer to set this number is larger or equal to the 2 lambda. And from this equation, degree phi is almost same as the Bn squared. We conclude we prefer to set degree phi is almost same as the B squared times 2 to 2 lambda. Okay, so from the first strategy, we find the relation between the degree phi and B squared. Okay, then next I explain the second strategy. And second strategy is a combined reverse attack and a median middle attack. And consider the length of the isogenies. And the first isogeny is the BBB isogeny. And second isogeny is also BBB isogeny. And the whole isogeny is almost the degree phi isogeny. So the gap between the V and V prime is about the degree phi over B squared. So we prefer to set this value as larger than the 2 to 2 lambda. So we prefer to set the degree phi is the B squared times 2 to 2 lambda. So we also have the same result by using the second strategy. So we conclude we prefer to set degree phi is almost same as the B squared times 2 to 2 lambda. Or I should say the LIT problems are hard when the degree phi is larger than b squared times 2 to 2 lambda. Okay, so this is a relationship between degree phi and b. Okay, then finally, I want to say why I focus on the LIT problem. And it is because we can construct the parallel isogenies with a small overhead. By the analysis, we know when let PQ be a torsion point of order 2 to B, and we can compute the parallel isogeny here. The length of it is about B. Then the degree of this horizontal isogeny is about 2B plus 2 lambda from the previous analysis. So we know that we can construct the not so big overhead. By using the not so big overhead, we can construct the parallel isogeny. So this is the reason why I focus on the LIT problem. Okay, so this is a summary of the LIT problem. The next, I want to talk to you about the ice cube new key encapsulation mechanism based on the LIT problem. And yeah, this is the core idea of the ice cube. Let P be a LC to C times LA times LB to B times F minus 1. And LA, LB, LC are small distinct primes, and F is a small integer. And here we need to set the LC to C is about 2 to 6 lambda. And LA to A is the 2 to 6 lambda. And LB to B is a 2 to 2 lambda. So the P is almost 2 to 8 lambda. So the LB to B is a small torsion, and LA to A is a kind of long isogeny here. And we consider that this box SIDH diagram. So this is the SIDH diagram. And vertical line is the degree of the B, so LB to B degree isogenies. And isogeny between the ES and shoulder ES is about LC to C minus LA to A. This number is not always smooth. And I'll explain how to construct this type of isogeny later. And the isogeny in this horizontal line is about LA to A isogeny. Then how does ice cube work is we first take ES and to the ES as a public parameter, and I'll compute the public key E1 by using the same technique as a CJ hash function. So we did not need to the exponent A here. So by using CJ hash function, she computes E1. And Bob computes the 3 vertical isogenies from to the ES and E1. And he gets ES prime and E and E1 prime. And he outputs the ES prime and E1 as a ciphertext, and let E be a shared key. And in the decapsulation, and I compute, I was using Kani's theorem and compute isogeny from ES prime times E1 primes to E times E2 prime. Then I get the shared key E. This is a very easy, very rough explanation of the ice cube. Okay, the next I explain more detail of this scheme. Let PC and QC be a basis of ES LC, and PB QB a basis of ES LB to B, and let degree phi I is LA to A, so it is almost same as 2 to 6 lambda. And let degree tau is isogeny of degree LC to C minus LA to A. Then at the beginning, we compute we compute the isogeny tau and the image point of tau PB, tau QB, and tau PC, and tau QC. Then these are the public parameters. So everyone know about the isogeny tau. And next, I will compute the isogeny phi I, and she computes E1 and phi p, phi I PV and phi I QP and alpha, phi I PC and alpha inverse phi I QC. So she didn't mask the part of the PV QB. These are the torsion of small orders, and she masked the points of the large torsion PCQC by using the scalar alpha. So she used here using the technique in the CSIT problem. And the public parameter is the EES, PVQV, and PCQC, and the isogeny tau. And the public key is E1, phi I PV, phi VQB, and alpha phi QC, and alpha inverse phi QC. And the secret key is this isogeny phi I and the scalar alpha. Okay, this is a public key generation. Okay, then next I explain the encapsulation. The encapsulation is compute the three parallel isogenies. So Bob takes the random value R, and he computes three isogenies, and kernel of the phi B is generated by PB plus RQB, and kernel of the phi 0B is generated by tau PB plus R tau QB, and kernel of phi IB is generated by phi BQB, phi PB plus R phi QB. And he computes the image point of these points, and he masked these torsion point by using beta. And the P and QB, PI and QI is public key of Alice. So these points are masked by hidden scalar alpha. So finally, these right side points are scaled by alpha beta, and left hand side points are scaled by beta. And the ciphertext of the ice cube is that becomes in the bottom line. So ES prime and beta, phi B, tau PC, and beta inverse, phi 0B, and tau QC, and E1 prime, beta phi IBP, and beta inverse, phi IB Q1. And shared key is the middle FT curve E, and secret key is the R and beta. And this is a key encapsulation. And finally, Bob sends this ciphertext to Alice. And this is a decapsulation. Alice got the ciphertext from Bob. And the right-hand side is masked by alpha and beta, and left-hand side only masked by beta. So Alice also masked this point by using alpha. Then these points have become compatible. And finally, she used kind7 and the kernel of the isogeny from ES prime times E1 to E times E prime is generated by alpha P0 prime, P1 prime, and alpha inverse Q0 prime and Q1 prime. So by using kind7, she can obtain the isogeny E. This is a decapsulation of the ice cube. Okay, then I go back to core idea slide. And yeah, as I explained, as I mentioned, the public parameter is E0 and Julia E0. And everyone know the isogeny tau between them. And first compute Alice, the isogeny of LA to A isogeny, and she obtained E1. And she output this decouple the public key and some other torsion points as a public key. And Bob computes the vertical three isogenies. And he outputs ES Julia and ES prime and E1 prime. And some other torsion points as a ciphertext. And finally, I will compute the Kani's theorem. I use Kani's theorem, and she obtained the shared key E. And this is the scheme of the ice cube. But there's a problem remains. The problem is here. The degree tau is LC to C minus LA to A. So this one is not smooth in general. So the problem is how do we construct a non-smooth isogeny tau? Then today I explained the method to use the structure of the endomorphism ring of the curve J invariant 1728. Then this is a very easy remark. That E0 will be a curve J invariant 1728. Then the endomorphism of E0 is represented by this as an order in the quaternion algebra over Q. So by using this structure, we can construct tau. So how do we compute the tau? First, we take the large integer n defined by the LC to C minus LA to A times LB to B squared. Then using Kronecker algorithm, we can find the integer z1, z2, z3, z4 such that z1 squares plus z2 squares plus q times z3 squares, z4 squares is equal to large n. So by using these values, we can find the endomorphism of E0 gamma, and the degree of gamma is equal to large n. And it is easy to see the gamma is separable. So we have the alpha can be decomposed 3 isogenies, the hat of psi prime and tau 0 and psi. Here, degree psi prime and degree psi is equal to the LB to B, and the degree tau is equal to the LC to C minus LA to A. So by using the diagram, we can find this diagram that this triangle is related to the gamma, and it decomposes 3 isogeny, psi and psi prime and tau 0. And we can easily compute this psi and psi prime because kernel psi is the intersection of the kernel gamma and E LB to B, and the kernel psi prime is the intersection of the kernel hat gamma and E LB to E. So we can easily compute the kernel psi and psi prime. Then we can obtain the gamma. We can obtain the ES0 and Chura ES0. And we also want to compute the image point under the tau 0. And it is easy to compute if the order P is the covariant to EB. We can compute the tau P0 by E over LB to B by psi prime gamma hat psi P is equal to the phi prime. So by using the hat psi here and using gamma and push psi prime, we can obtain the image point of the tau 0. The problem is that we also want to compute the image point of the LB to B torsion points. So the problem, how do we compute this image point of these points? Okay, the answer is using the Kani's theorem. Let PC0 and QC0 be a basis of ES0, FC to C. And here we assume that A is even for simplicity. Then we can find this SIDH diagram. The horizontal is the tau 0, and the vertical lines are the scalar multiplication by LA to A over 2. And by using Kani's theorem, we find the psi 0 defined by this matrix. And its kernel is defined by generated by LA to A over 2 PC0, tau 0 PC0, and sorry, there's a missing something here, but LA to A over 2 QC0 and tau 0 QC0. So we can compute psi 0, and psi 0 have the information of the tau 0. So by using psi 0, we can compute the image point of PB0 and QB0. Here, PB0 and QB0 is construct the basis of the LB2B torsion subgroup of ES0. So finally, we can compute the all image points we want. But there is still problem remains. And the problem is that ES0 and E tilde ES0 are not random curves because it is generated by the gamma. It is an endomorphism of the curve of J invariant 1, 7, 2, 8. So we don't want to use these curves. So I need to explain how to randomize these curves. At the beginning, we have these points, ES0 and PC0, QC0, and PB0 and QB0, and image of the tau 0, tilde ES0 and tau 0 PC0, tau 0 QC0, tau 0 BP0, tau 0 QB0. And first, we compute the two parallel LB to B isogenies using PB0, QB0, and tau 0 PB0 and tau 0 QB0. And we compute the image points of them, and we obtain the LES1, P prime C1, and Q prime C1, and to the ES1 and tau 1 PC1 prime and tau 1 QC1 prime. And next, we randomize these bases by using the random regular matrix A. And finally, we compute the image point of tau 1, image point of the LB to B torsion points by using the same method to recompute the tau 0 PB0, tau 0 QB0. So we use Kani's theorem and the points of PC1, QC1, and tau 1 PC1 and tau 1 QC1. And we can compute the image point of the LI to be torsion points. And finally, we output ES1, PC1, QC1, BP1, and QB1, and the image point of them. And here, by randomize here, the PC1 and QC1 is a random basis, and BP1, QC1 is also random basis. And repeat the above procedure many times, we can obtain random empty curves as a starting curve. And represent this procedure as a diagram, and it can present like this. So we can compute the parallel isogenies of degree LB to B, and we can obtain the random, the image point of random bases. And repeating this procedure, finally we get the random metric curve E0 and random basis PCQC, PBQB, and the image of the isogeny tau. So by using this method, we can randomize the starting FD curves. Okay, so these are the construction of ice cube. Then I finally explain or show some properties of the ice cube. And this is a parameter size for ice cube. When the security parameter is 128, the P is about 10,000, 44 bits, and the security parameter is 122. The P is about 1,558. And when it is at 256, it becomes 2,068 bits. And as you can maybe easily check that these values are almost same as the 8 lambda. So the prime P, the size of prime P is almost 8 lambda. Okay. Then we can also compare with the size of the cyc. then we assume that the prime for psych has a size of 4 bits. And then for psych, the size of the original cycle public key is about 24 lambda, and the compression version is the 14 lambda. And for ice cube, public key of original one is the 18 lambda, and the compressed one is the 40 lambda. I didn't explain about the compressed ice cube, but we can use the same technique for the compressed SIDH to ice cube. Then this is a result for that compression. And for ciphertext, the original psych is size of the 25 lambda, and the compressed version in the 20 lambda. And for ice cube, the ciphertext about the 96 lambda, and compressed version is 68 lambda. So the public key of the ice cube is about 3 times larger than that of psych, and the ciphertext of ice cube about 4 times larger than that of psych. So this is the size of the public key and ciphertext of ice cube. And finally, I show the result of my proof of concept implementation. And this is a result for proof of concept information by a stage mass. And I measured the average of this time about the average of the 101 times, except for the public parameter generation. We only compute the public parameter generation at once. So this number is, you think this number is just the reference number. And we use the MacBook Air with the up to MI CPU. Then as shown in this table, the public key generation is a little bit not so fast, and key encapsulation is not so bad. Key encapsulation is a little bit heavy as my proof of concept implementation. Okay, my talk is over. Thank you for listening. And sorry for sometimes my English is messing. Is there any question?
Thank you very much, Tomoki, for a fantastic talk. As always, yeah, if there's any questions, just unmute or type them in the chat. And while people are maybe typing, maybe I can ask a question. So I wondered, like, for the lit problem, did you consider like maybe almost like information theoretical argument that 2 to the 2 lambda should be enough, at least assuming that the like no torsion point information problem is hard, basically, like, because if you have like big enough degree isogeny, then these torsion point images can't like uniquely identify each isogeny. I mean, there are more combinations of there are more isogenies of a given degree than there are like combinations of torsion point images. Am I making any sense? Is this actually making any sense?
So sorry, and so what is your question?
Yeah, just if you like considered some kind of or if there's an argument like this, or for why this lit problem is hard.
Okay, and so you want to ask why I think the lit problem is hard, right?
Yeah, or like if you could like somehow argue, but maybe it's a weird question anyway. Just because I thought maybe, okay, so if there are way more isogenies of degree whatever A is, then there are ways to get different torsion points. Basically, there will always only be B squared, like less than B squared possible torsion point images, right? So if the degree is much more than B squared, maybe you could argue somehow that yeah, maybe, okay, this is probably not making any sense. It's it's a weird question.
Okay, thank you.
Sorry.
Well, sorry, I didn't think about such kind of thing, so
Okay, no, it's probably not worth it. So Boris has a question. Boris, are you raising your hand on purpose or?
Can you hear me now?
Yeah.
Okay. Yes, thanks for the talk. I had one question, which is about the problem in the scheme and the problem and the lead problem. Like I felt like in the scheme, you reveal some small exact torsion and then you revealed some other torsion up to the scalars, right? So is it really the lead problem or is something different? Like here, for example, you have phi of PB, phi 1 of PB, phi 1 of QB, and then you still have phi 1 of PC up to a scalar, and then phi 1 of QC up to the inverse of the scalar. So this is like lead plus something plus more information.
Yes, I didn't explain, but yeah, this is not exactly the lead problem. It is easier than the problem because it has the information of the other torsions. So yeah, so I should say this one, the lead plus CSIT problem or something.
Okay, yeah. So, and maybe for the generation, I don't like, maybe it just taking a gamma of larger degree would make the curve be random from the beginning already, rather than taking smaller degree and then doing another random walk later, maybe. But then you have to do ideal to isogeny translation somehow, or translate a very long ideal into an isogeny somehow, I think.
So sorry, what you mean?
Like in the key generation where you do the, you take the gamma of degree to LB to the B squared times tau, what was the degree of tau? LC to the minus LA, something like that. The degree of your gamma in the key generation.
Gamma. What you mean gamma is this gamma?
Yes, the n here. If, for example, you take n instead to be LC minus L A to the A times something which is the square of what you need to get a uniformly random curve in the graph, then you are already sure that your gamma is somehow uniformly random, right? Or
so I don't understand what you're saying, but you mean that from the structure of the E0, we can prove that this E0 is random or something?
yes, if for example psi and psi prime are already random enough from the beginning, long enough in the beginning, then you can also claim that your isogeny is random. But then you will not just compute it by intersecting the kernels. You will do many steps in computing psi and psi prime somehow. But yeah, we can discuss this later. It's just a little remark, but yeah.
Okay, thank you.
Okay, awesome. There's also two questions from Anael et al. First one, I think I saw Bruno go up and ask, so I'll credit this question to him. Sorry if that's wrong. So the question is the starting curve in the public parameters random in the sense that its endomorphism ring is completely unknown?
I don't know what you mean the complete tree, but unknown or we cannot get the information for, or we think is more precisely, but we think it is hard to get the some information of the endomorphism ring to use the compute or solve the isogeny problem. Yeah, so the information on the endomorphism ring is can be used for the solving the isogeny problems sometimes. So yeah, so non-static count means but completely unknown is not true because, for example, the scalar multiplication is endomorphism, and we know that Z it is a subring of the endomorphism ring, but For the sense of the solving the isogeny problem, we think it completely unknown or similar. I
Yeah.
don't know is the answer of it. I don't know. I'm not sure, but
Maybe a comment if Jonathan allows me. Maybe the question is
Allow you.
your setup public or trusted? Like the works phi, psi, and psi prime, do you assume they are public or do you assume that they are secret or somehow? Maybe I understand the question.
I assume that this random walk is hidden, or I assume this is hidden.
Yeah, cool. I can also ask the second question from France, which was maybe from Pierrick. I'm sorry if this name, if it's completely incorrect who's asking these questions. Anyway, the question is, what type of implementation / code do you use for the two-dimensional computations? So do you use like theta model or Richelieu isogenies? So...
Okay, I use the Richelieu isogeny, so I guess there's a possibility to become more faster by using theta coordinate, but I'm not sure. And yeah, it used the Richelieu isogeny.
Yeah, cool. I thought the timings were quite impressive. It looks surprisingly fast for like a Sage math code. It was very cool. Okay, are there any more questions? If not, I think we can finish the meeting or the recording at least.